So in order to come to the information gain, we first need to define the concept of entropy. And entropy, the way we can think about it is called what is the smallest possible number of bits on the average that we have to transmit or per symbol to encode, such that if we get a symbol that is drawn from the distribution of X, right? So the idea is, in some sense, how much noise or how much bubbly is the distribution X. So the idea is, how do we measure the entropy? We say the entropy of a given distribution X is simply a minus summation over all the possible values this distribution takes, the probability of it taking the jth value, log again the probability of taking the jth value. And the intuition is very simple, right? If I have a distribution that has high entropy, this means that the probability distribution of X is uniform, right? In some sense, it's boring. It's like everything is flat, everything has the same probability. So if I would create a histogram, the histogram of this distribution would be just, right, it would be this kind of flat line. For example, distributions of low entropy, they are interesting. They have many peaks, right? So the idea here is that if I plot the histogram of a distribution with low entropy, this distribution would have a high peak and the rest would be very low, right? So in some sense, if a distribution has very high entropy, it's very hard to guess the value of X. And if a distribution has very low entropy, then it's very easy to guess what's the value of X. So for example, here at the bottom, imagine I have a distribution of dots on the plane. For example, here on the right, where I have these dots kind of uniformly spread throughout the space, this is the condition of high entropy, because for me it's very hard to guess where the dots are. But in the case on the left, where I have all the dots in one part of the space, it's very easy for me to guess a location of a dot, right? So this is the case of the low entropy. So basically the idea is that entropy measure tells us how uniform or how spread out or how boring is a given distribution. And if the entropy is low, then the distribution is very peaked. Kind of it always takes the same value. So the distributions that have low entropy are very, in some sense, easy to guess, right? So now that we have the concept of entropy, let me give you an example. So imagine that I want to predict value y, but I'm given input x. And in particular, imagine that X is the college major and Y is whether the person likes Gladiator or not, right? So my data is a set of XY pairs where X is the major, Y is whether the person likes the Gladiator or not. So now I could start asking, okay, what are some entropies in this case? For example, imagine that I want to ask, what is the entropy of Y, right? Computing the entropy of Y is easy. My Y takes two values, yes or no. So first I need to ask, what's the probability of Y taking a value yes? Then I need to say if this is 0.5, so 4 out of 8 cases is yes. So it's 1/2 times log base 2 1/2. And then I also need to say how often does the value Y take the other value, the no value. So it's 1 minus 0.5 in this case. So it's another 1/2 times log base 2 of 1/2. So overall, the entropy of Y is 1/2. In a similar way, I could also go and compute the entropy of X. X here takes 3 different values, right? Math, history, CS, and that's it. So now here I would say, what fraction of times does the X take value of math? Take those probabilities, multiply it with the log. What fraction of times does it take value CS? And what fraction of times does it take value of history? So that's the idea how we compute entropies on a given data set. So now that I discussed how do we compute the entropy, now we can introduce the concept of a specific conditional entropy. So the idea here, the way we write this is the following. We say, what's the entropy of Y given X takes a particular value V? So this is the entropy of Y among only those records for which X has value V. Right? So for example, if I can ask, what's the entropy of Y given that X takes the value math? So what would this mean is I only go select the rows for which X takes value math. I see that half of them have value yes, and half of them have value no. So using the same calculation as we just did on the previous slide, the value is 1. For example, I can ask, what's the entropy of Y given that X is majored in history? So I'm taking all the history entries. Here they are. Both of them have value no. So this is a completely boring distribution, right? Everything is the same all the time. So historians don't like Gladiator, which I can kind of conclude based on this small example. Similarly, I could also compute the entropy of Y, so whether somebody will like Gladiator based on whether they majored from computer science. So now this is what we just did is specific conditional entropy. And the reason why it's called specific is because we are conditioning on X given or taking a particular value V. We can generalize this concept and call and define the conditional entropy. The way we compute conditional entropy is very simple. All we do is we go over the domain of a given variable X. We say, what's the probability of X taking this value times the entropy of Y given X, right? So this is the entropy of Y given X. It's simply the weighted average specific conditional entropy of Y, where weights are the probability or fraction of times X takes a given value Y. So let's look at a simple example of conditional entropy. The idea here is we say that conditional entropy of Y given X is the average specific conditional entropy of Y. We have the formula. So for example, if I take my input data table here on the left, I can create the conditional entropy table where my goal is to compute what is entropy of Y given X. So for every value of X, I need to compute what is P of X. I have it here. And then for every value of X, I also need to compute what is the entropy of Y. For that given value of X, I get this table, and then I just do the weighted summation, and I would find that the entropy of Y given X, in our case, would be 0.5. So now that we have kind of built all the machinery, we are now ready to talk about the information gain. And information gain, what it tells us is the following. It tells us if we want to transmit Y, how many bits would we save on average if both ends would know X, right? So the idea is what is basically the difference between what is the entropy of Y and what is the entropy of Y given that we already know X, right? The bigger the difference, the more X tells us about Y, right? So Y is our class. We see what is our entropy of Y, and then we say, how much would this entropy decrease if I go and tell you X ahead of time? And for example, in going back to our case, to our data table, we already know that entropy of Y equals 1. We already know that entropy of Y given X equals 0.5. So the information gain of Y given X is 0.5. So basically the idea is that in our case, what we will do is we will, for every feature X sub I, we will go and compute what is the information gain of Y given X sub I. We will then rank our features by the decreasing information gain, and we want to pick features that have high information gain, right? That tell us a lot about the value of Y. So just to give you an example how to think about this, imagine we are trying to predict whether someone is going to live past 80 years, right? So we have this prediction problem where we say, are you going to live more than 80 years or not? And imagine that using some historical data, the information gains we would compute would be something as follows. If I say probability, what is the information gain of long life given the hair color? Here the information gain is very low. Basically, hair color doesn't tell us much about the probability how long is someone going to live. For example, we see that whether somebody is smoking or what is someone's gender tells us much more about how long somebody is going to live. For example, given that social security numbers in the United States are random, so how much do last 4 digits of social security number tell us about how long is somebody going to live? They don't tell us anything. So the whole idea about information gain is that it tells us how much information about the target variable Y is stored or contained in X. So basically the attribute Y that has high value of information gain is the attribute on which we want to split when creating a decision tree in our case.